we look for specifically in the packet traces. And one of the reasons why we named this session the way that we did is because there's so many times that people run into issues where the network is being blamed. I mean, come on, that's what people blame right away, isn't it? I mean, most of us actually, can I just get a show of hands? Do you mind telling me, are you from the network side? Network engineer side, okay. How about server support, application, okay. So most of us are network people, right? So we're probably in this room because we're sick of getting blamed. Now, people blame the network with or without cause, with or without any type of data to back that up. I always think it's interesting for me when I'm calling in to make a change to a flight or talk to my bank about something with my account, and the person on the other side of the phone tells me that they're having network problems. So how's the weather, whatever, you know, they do that stall thing. Have you ever had that happen to you? Happened to me not long ago. I just had to make a quick change with my flight. And the person who was in that call center I could tell they were stalling. They were doing something. And even they were blaming the network, which I always find that interesting because they're just working a call center. And I mean, how do they know what the real root problem is, right? All of us can think of 100 things that we could go try to troubleshoot, but even a non-technical person is blaming the network. So what's happened culturally is it's put us in this defense mode where now we're trying to get the blame off the network. Well, that's a nice thing to do, to be able to get the blame off the network and show them, no, this is a application call that's taking 60 seconds. See, it's not my network. But the thing is, as network engineers, that's where we need to get to. We need to get to not just saying, okay, it's not my network, but also show them specifically what is the problem, and even better yet, help them, or if it is us, get to root cause and resolve it and make it go away. Now, one of the reasons why we're here, one of the reasons why we're getting blamed and just culturally as network engineers, well, we're responsible for the lower layers of the OSI model. So if you go to HR and you pull up our job description, we're responsible for the physical layer, we're responsible for data link, we're responsible for routing. You could also put a toe up into the transport layer and say we're responsible for load balancers and for firewalls and things like that. But as far as owning and embracing things above those layers, a lot of times it's just not our problem. It's not what we're responsible for resolving. So when a problem strikes, what do we do as network engineers? Typically, we make sure that our connections are okay, we're not blasting traffic anywhere, capacity isn't a problem, that we don't have a ton of errors on any ports along the way. And if all of those things are checking out good, then hey, thumbs up, the network's fine. Especially if we can run a throughput test from one point to another, things are looking great, data's passing. Okay, show me why it's the network. Well, network looks good. On the other end of the spectrum, we have our server application guy, and he's responsible for the upper layers. So the actual service that's supporting the application, he's responsible for making sure that thing's up and cranking away. If there's a problem, then he's going to check into his system. I don't know what monitoring tools he might be using. Check for server resources, make sure that the service is running in the first place. And if he doesn't see some major indicators, then he's just going to blame the network. They're going to blame the network anyway, but they're also going to hopefully do a little bit of due diligence on their stuff. But if you notice, there's an important layer that we jump over. And this slide this just shows culturally what I see all the time as an independent third-party analyst. I just see people in boxing matches over the transport layer. I'm not saying that all problems are in the transport layer, but the transport layer is an often unowned, it's not an owned thing. People don't own it and embrace it and say, yep, that's me. I'm responsible. I'll take ownership of that. So today, what I'm going to show you is how to do that with packets. Start at the transport layer, take a look at how things are performing at that layer, and then that will help us to saw the OSI model in half and either go up the stack or down the stack, depending on what we find at that layer. All right? So from this point forward, for the rest of your careers, you guys are going to be owning and embracing and taking responsibility for the transport layer, which Wireshark is going to help you to do. So, all right, let's go ahead and talk about some specific things that we're going to look for at the transport layer that indicate network problems. So just to show you in the, or to tell you how we're going to do this, I'm first going to show you some examples of some network issues, some actual network problems and indicators that we're going to look for in the packet level. Then I'm going to show you an application problem, something that was actually due to the application not responding very well. And then I'm going to show you what I call just TCP weirdness, some things that can happen at the transport layer with the TCP protocol that can be tough to find and aren't necessarily network, and they're not necessarily application, but they're in that middle space. All right, so first of all, before we take a look at a single packet, just a few things that we want to make sure that we do before we get there and get lost in the weeds. First, we want to define what is it that we are troubleshooting. Is it performance? Is it I can't connect at all? See, the word slow, when people are complaining about slowness, that's a whole lot different than I can't connect at all. Right away in your mind, you should be thinking, okay, if they can't connect at all, it's not working at all, I'm going to look for different symptoms in my trace file than I will if it's just slow from time to time. Those are two different problems. We want to define that well. Next, it's always slow versus it's sometimes slow. Those are also two different types of problems that we want to dig for. And the third one, it only affects Jim versus it affects everyone. So just a tip, if you don't have a clear picture of those three scenarios before you start digging into your packets, just stop, back up, ask questions, ask the users, really get input from them, get information, really make sure you have a good picture on the behavior of the problem before you go packet digging, because as we know, it's easy to get lost in those weeds. All right, so, and then also make sure that we capture in the packet path when the problem is happening. I'm sure you've had this before as well. You're looking through a trace file and you find that everything's working just fine. And that the capture actually wasn't taken when the problem occurred. Actually, that happened to me last week. I had someone send me a trace file. They said, here's a problem that we were having. I said, okay, when did you experience the problem? Oh, last week, the week before. But here's a trace file from today. I was like, well, we got to capture it like when it happens. So otherwise, we're just looking at what could be perfectly normal performance. Which, by the way, is nice to have. When we're looking for broken, it's also nice to have a trace of things that do work. Because then you can take a look at the calls and take a look at the conversations that happen when things are performing normally. All right, so let's take a look at some things that happen, and these would be more network-related issues, okay? So these are the big ones. We want to look for things like retransmissions. We want to look for out-of-orders, duplicate acknowledgments, high latency. Now I'm going to bring up a trace file and show you how to look for these indicators and what they mean. But typically, these are the types of things that we're going to want to watch for if we're trying to look for a network issue. Or if we see these in our trace files, that's when our mind can begin to go in that direction. Okay, so again, retransmissions, out-of-orders, dupacks, high latency. Now these are if we're using TCP-based protocols or applications, if they're using TCP. If we're using UDP, we can talk about that in just a minute. But first I'm going to show you some examples of what those network problems look like when we're using TCP. All right, so enough slides. We didn't all come here to see slides. We want to see packets, right? So let me open up my first trace. All right, just simply this one was a slow download. And let me come up to the top here. All right, so before we dig. Okay, so this was just a user going out and downloading a file, and it was slow. It was to a server that was not on their local network. So right away, just from the beginning of this trace file, or let me tell you a little bit about my profile that I have here. Now first, we have our packet number, right? So next to that, we have our running total of time. That's how I have my time column configured. So this is starting at 0, and I'm going from 0 up to the end of the trace file. That's the one that I like to keep there. Next to that, you notice delta time. Now you're going to see delta time on just about every instructor screen that we have for Sharkfest. So that's something that you absolutely want to add. Delta time tells you the amount of time between packets, or amount of time from the end of one packet to the end of the next one. Now for me, that's the delta time displayed. So whatever is actually here, that's showing me the time between those frames. So if this isn't something that you have added yet to your Wireshark profile, absolutely something you want to make sure is there. Now, how to do that, Betty just showed us in her session earlier this morning. On my YouTube channel, I have a quick way to do that. You can go out to Packet Pioneer on YouTube. I shot a little video of how to add that. But quickly, that's where you can just come down to frame and time delta from previous displayed frame. This is where we can add this as a column if we'd like to do that. So, let me come up here. Okay, delta TCP conversation. That's my third time column that I have. Now for me, this is useful because what this shows me is this is where this packet falls in its TCP context. All right, so if I have a trace file and it's got a lot of different TCP connections happening at once, which is the case in a lot of scenarios, right? We don't just establish one TCP connection to a server and do everything over one connection all the time, right? So especially if we're going out to a website or if we're pulling a lot of different connections, this is a useful timer to have because as soon as I start to capture, I'm going to see packets from several different connections interleaved, right? The packet above me doesn't necessarily relate to the conversation that I'm on. So to save myself from filtering every single connection and sorting on the delta time and seeing where those delays are, I can just add that time column, and what that does is it shows me in context where did this packet fall in its TCP conversation. All right, so that's a really useful one for me to add as well, one that I like to use. That's one I could recommend to you. To add that, I'm going to show you real quickly. To add that guy, I'm going to minimize my internet, or that IP layer. I'm going to go to TCP. Now for me, previous to this, I right-clicked TCP, I went into protocol preferences, and I went ahead and I selected calculate conversation timestamps. So in order to add the field that I'm about to add, you have to make sure that you do this as well. That's an important one. Once you do that, you're going to notice in the TCP header that you have at the bottom timestamps. So if you don't have that checkbox checked that I just showed you, this will not be there. Once you have timestamps, now you can say time since first frame in this TCP stream or time since previous frame in this TCP stream. This is the one that you can add as a column. Now I'm going to show you, just so you know what that column is, I'm going to show you in a couple of the trace files how that really made a difference in finding the problem. Okay, so for me, this is the way that I like to set up my timers. It's useful and helpful for me to get in to see where the delays occur in the trace file. And we didn't have Hansong this morning, but usually when he does his presentation, he just says, look, this is my way or the highway. So this is the way that I like to do it. You're going to find your own Wireshark style, the different columns that are useful to you, and that really can help you get to root cause. So these are just mine. All right. So let's go ahead and take a look at what's going on up here. So first of all, we might notice, for me, I just like to color my sins bright green, right? The TCP sins. So I went into my coloring rules and I said anything with the sin bit, let's go ahead and set that green. For me, that's helpful. I find this person, this user, he's going out to a server 10.0.0.1, hitting port 80. And if I scroll over here, I can see this is the sin. If I come over here, I see my SYNAC come back, and right away I see that I have 167 milliseconds that it took just for the client to get there and then to get that SYN back. So right there, this is a very important number to know. Anytime you see a TCP handshake, look at the total amount of time between SYN, SYNAC, and ACK. That's your basic network round trip time. Now for this, I was capturing client side. If I'm capturing server side, then I'm going to see that delay between SYN and SYN-ACK. If I'm capturing somewhere in the middle, then I can add those two delta times together to get that full round trip time. All right? But client side, so I see my delay, my round trip delay is 167 milliseconds. Now, hey, we're network people, right? 167 milliseconds doesn't seem too good, does it? Seems pretty slow. Most people would say, oh, well, of course it's slow. Look at your round trip time. But we want to be careful against saying things like that are a bit too sweeping of a statement. Yes, this is not fast, but is this my root cause yet? No. No human being is going to punch their screen after 167 milliseconds. Do we agree? Their complaint was slow. They went and hit a file, and it was taking a minute to download that thing. So I haven't found my root cause yet. But I have found that my network round trip time, client to server, is about 167 milliseconds. Note to self, write that on the board. All right, that may or may not be related. Okay? All right, so then the handshake completes. We see our get, and then we see an ACK come back from the server 155 milliseconds later. Now let me back up here just to this 167. One other thing that I like to do is I like to take a look at the TTLs in the IP header to take a look at how many hops I have between client and server. All right, so 167 milliseconds. If this server was one hop away, if I just had to go one router and then back in 167 milliseconds, that would be a big problem, wouldn't it? But if I have to go several routers, well, this is a different story. So how can I tell from the packets? Well, if I take a look at that SYN-ACK, this is the one that's coming back to me, and if I come down to the IP header, this is where I can come down to our TTL, time to live. So that field is very useful for us to figure out where are we in the capture stream, in the packet path. Here, this packet coming toward me, every time that it crossed the router, that number was decremented by 1. If that number ever goes to an actual 1 and gets decremented to 0, the router that decremented it will not forward it. Instead, I'll get an ICMP message back saying, hey, your packet died. It was, too many hops. So eventually, this packet's going to die after 55 more hops. Thankfully, I received it before that happened. But with the TTL field, these guys usually start at bit boundary numbers. So things like 64, 128, 255. So if I take a look at my SYN, the TTL on my SYN was 64. The client sent 64. So every router along the way decremented that number until it was received by the server. The server turns around, fills up its TTL, whatever number it's using, and as it crosses routers coming back to me, it's decremented on the path back. So 55, let's just use some logic here. The receiving TTL on this packet is 65. Now what's more logical? Either this packet started at 255 and this packet came through 200 routers on its way to me, and there are literally 200 routers between me and that server. That's one possibility. Or it started at 128 and it came through, 70-something routers on its way to me. Or it started at 64 and it went through, 9 routers on its way to me. Unless there was something on that side that was tweaking with that number. So what's the more likely scenario there? I can make a pretty educated guess. This guy started at 64. Am I absolutely sure of that? Not without capturing on the server side, but I can make a pretty educated guess that packet went through 9 routers on its way to me. So now I can take that assumption, which is, it's still an assumption, but you could say it's a good one, and I can take a look at that 167 milliseconds, and I can say, okay, 9 routers, how many of them do I actually own in my enterprise? 1, 2, okay, then I hit my, okay, I own the first 2, The other 7 are in my ISP or wherever else, right? So we can start to figure out, okay, that delay isn't necessarily all my fault in my system. It's going off somewhere into a network that I can't control. All right? So that's a good number to keep in mind with our TTL. All right, so here's our get. We need acknowledgement back for the get, and then we see our okay. So this application, if I take a look at from the get to when I start to actually begin to receive data, here's my 200 okay, I'm still only a couple 100 milliseconds here, or 155 milliseconds and change. So far from the capture start and to when I'm actually receiving data from that server is only 327 milliseconds. Question, is the end user punching his screen just yet? 300 milliseconds as a human? Not quite yet. But I can see that the connection's established, it's not being blocked anywhere, I can take a look at the round trip time, and we can move forward from here. All right, so from now, to save ourselves from scrolling, what I want to do, I'm going to come over here to our delta time. Actually, I'll go ahead and do it. Both of these are the same, so this is just one connection. I'm just going to sort on this guy, and let's go to the top. And here I see a delta time of 16 seconds. All right, what kind of packet did that hit on? A TCP keep alive. All right, so at some point in this conversation, I had a 16-second pause. That's more something that someone would complain about, right? That's screen punching packet timing. Interestingly enough, the packet below it is half that time, 8 seconds. Packet below that, 4, 2, 1, and then I get into these hundreds. All right, so this is something that I'm going to want to start to investigate. This at least gives me an idea of where I want to start digging. It may be that these happen at the end of the connection and they're unrelated, but we don't know that just yet. All right, so let's take a look at our 16 milliseconds. We're going to go ahead and resort. We got a bunch of ugly stuff going on here. Before I get to this, though, I just do want to come up here. Above that point, that pain point that I was on, above that, if I come over here, I've got dupbacks, I've got previous segment not captured, I've got some retransmissions, I've got out of orders. In fact, I could come up here to this little button, bad TCP, and just filter. That's TCP.analysis flags. It's absolutely something that you want to add to your Wireshark, bad TCP. Because that'll show you, that's just what I call it, TCP.analysis flags. So that will show you retransmissions, out of orders, dupbacks. It'll show you all the TCP ugliness, and it'll put it in black and red. So this basically shows you that you have some packet loss. There is some retransmissions happening, so packet loss is occurring. So right now, we would start to head toward that network problem. We want to start to investigate where those packets are being lost. So we do see some bad TCP. We do see some retransmissions out of order, some other ugliness. But if we take a look at the timing, I'm just going to undo my little filter. Okay, I'm going to go back to that 16 seconds in just a minute. If I take a look at the total amount of time over here on my time column from the beginning of when I started to capture this trace file, if I start doing just a little bit of scrolling, not too much, I can start to see just a second in, 2 seconds in. That's where I start to hit some ugliness. All right, so we can see that we do have some issues in terms of dupbacks. We see we have some packet loss, some retransmissions, some things that aren't looking too good. But if I'm scrolling, I'm going to come down on my little intelligent slider bar. You can see this big, thick, black part here. I just noticed that when I was filtering on it. That's where that 16-second delay is down here. Just above that, I'm looking okay. Up until that point where I see that ugliness, I'm still only 3.6 seconds into the trace file. So I saw the connection, I saw the request, I got the response begin, the data starts streaming toward me. Only about 3 seconds in, between the capture beginning and 3 seconds, I did see some retransmissions and some ugliness. But is the person going to pick up the phone and call me 3 seconds into a download and tell me that things are slow, they're punching their screen. 3 seconds, they'd probably cope with that, right? I do see retransmission, but is that what the person is calling me about? Probably not. So let's go ahead and keep going here. So I come down to this big area of ugly black. All right, up here, data is moving. Things are cranking along. I see big packet from the server, acknowledgement, big packet, everything's looking good. And all of a sudden, I come down to this packet, 363. This is from the server, and if I have, let me go ahead and move my info over so you can see that a little bit more. Actually, you know what, I'm going to take you out. Let me just remove this guy. Give me some more room for my, where'd it go? There we go. Okay, big stuff coming over, big packet, and I hit this one from the server. This is a window full. Okay, so window full. We're going to talk about what that means in a second. After that, I get TCP 0 window from the client. Okay, after that, I see this keep alive. This is the server checking in 600 milliseconds later, 667, the server saying, hey, are you still there? Are we keeping this connection open? Talk to me. Just tell me something, because I haven't heard from you in 667 milliseconds. The client goes back 36 microseconds later saying, yep, I'm here. By the way, my TCP window size is 0. Let's talk about that for a minute. So a TCP window is basically a TCP receive buffer. I'm telling the server, this is how much space I have in my TCP receive buffer or window that you can send data to me unacknowledged. All right, that's a number that we're going to see in the TCP header. So I'm going to actually take a look at that. Let me expand this guy out. I want you guys to take a look at this TCP window size value. Now, we're going to actually work with the calculated window size. Unfortunately, I don't have a ton of time to talk to you about how that's set and the handshake, but this is the number that's actual, the real number that we're working with for our TCP receive window. All right, I'm going to go above this just a little bit. And what I want to figure out is the client digesting data out of that TCP receive buffer as fast as it's coming in? So the idea behind that TCP receive buffer is I can receive it, I can tell you how much space I have left to receive more incoming data, and if my TCP receive buffer ever fills, then I'm going to tell you 0 window. Don't send anything else. That window, that 0 window, is a way for the client to say, look, buddy, you're sending a lot of data, and I'm not processing it as fast as it's coming in. I'm stuck in some way. You got to slow down. So the client here, let's take a look at these big packets coming from the server. Here's 1514, 1514. Let's just take a look at one of these acknowledgments. This is above the point of the 0 window. All right, here I've got calculated window size 23360. I could add this as a column, but I don't want to add more stuff up there. All right, 23360. Okay, the server sends 2 more packets. And look at this number here, 2440. So that tells me how much space I have left, how much remains in my TCP receive buffer on the client side. All right, this is whoever is sending it. That's the one that's advertising that number. Well, we get 2 more big packets come from the server, and then we see 17520. You see what's happening? This number is going down. That means that this buffer is filling. The server sends 2 more packets. Hey, you're good. I can fit 2 more packets. Or this was actually in the stream, but client says, all right, 14,600 bytes. That's all I got left to receive from you. Server sends 2 more. Client says 11,680. We see what's happening. This number is dropping. 2 more big packets. So the client says 8760. 2 more big ones. Client says 5840. I'm almost full, server. 2 more big packets. Client says 2920. Then the server sends 2 more big packets. Now, if we do the math on that, he sent exactly the amount of space that I had left in my receive window. That's why Wireshark advertises to us, TCP window full. This is not the fault of the server. The server did send enough traffic to fill that window. Hey, there was space there. It's not necessarily a problem per se that the server isn't the one that's broken here. It just filled the client window. All right, so now after those 2 packets, now the client comes back and says, you know what, my window size is 0. Stop. Now the server can't send any more data until this number goes back up. Okay, so now we take a look at this 667. This is the server with basically a probe. It's saying, hey, what's going on, man? Are you still there? Are we still talking? It's been over half a second. Haven't heard anything from you. What's going on your side of the connection? Client comes back. Window size 0. I'm still full. I haven't digested my dinner yet. Still got a full stomach. I can't take anything else. So just chill out. Server says, all right. 1.133 seconds later, it doubles the amount of time. Server comes back. All right, how you doing now? You there? Can we talk? Can I keep sending you stuff? Client says, 0 window still. Look, man, I'm full. I'm doing other stuff here. I got other processes that I'm working on. I'm not worried about this little TCP buffer. I'm not emptying that thing out yet. Client or the server side doubles. 2 seconds now. Hey, how we doing? What's going on? Client, 0 window. 4 seconds later. Hey, what's up? How you doing? Can I start sending anything else yet? Nope, still 0. 8 seconds later. See now how we start getting into human time? This is human being time. This is screen punching kind of time. And all of this is, all these delta times add up over here in my time column, right? So finally, 16 full seconds, he sends this keep alive. I come back, I say, look, I'm still 0. And then shortly after that, my TCP buffer clears. I do a window update saying, hey, I'm starting to get some window here. And then finally, I update it all the way up to 256K. So this pain point here, that's screen punching worthy, isn't it? Above this point, I have retransmissions. I have some stuff happening on the wire that I don't really like the look of. I've got dupbacks, retransmissions. But TCP is recovering up there. Down below this point, I also have some retransmissions and some ugliness and some stuff going on. But this period of time is likely what that end user is complaining about. Right? So while we do see some network stuff, if my customer sent this to me, I could say, yeah, we are getting some network drops, but honestly, it's not the network. Right? We do see some packet loss. We do see some ugliness happening. But this client, he's stuck. He's not processing this data as fast as it's coming in. Now, to help us visualize something like this, another thing that you want to make sure you use, especially when you're looking at large transfers of data, if you find that those large transfers are going slow, then a graph you want to be sure to learn and use. You can find it under statistics. We can come to TCP Stream Graphs. Let's go to Stevens. Our Stevens graph. So what this shows me, it graphs it over time. These are our sequence numbers going up over time. So TCP sequence numbers, the amount of data that's going from one side to the other. We saw there was this initial burst of stuff going, and then I got that long pause. And then it takes off, not super pretty, but it takes off again and then goes up. What I want to see is a nice straight line, boom, going straight up. I want to see this guy just go straight up to where it hits the word Stevens. Then my download's only going to take me, 20 seconds or so? But here I saw a big period of time where there was nothing going across the wire. It just got stuck. So that's the kind of delay that I want to go watch for. So this is just an example. I like to show this one because when we first started looking at it, it's easy to say, oh, we got retransmissions. It's the network. which is true. There is an element of truth to that. We do see some retransmissions. We saw those things. But the thing that was really causing the delay, the thing that was the issue, was that stuck TCP window on the client side. Its TCP receive buffer was filling, not processing that stuff out as fast as it was coming in, and that is what led to the time, the real delay that the client was complaining about. So what kind of things cause that? A lot of times that client's busy doing something else. It could be stuck on some other process. It could be doing some kind of backup, some antivirus, something. But on that side, just think in terms of why would resources not be sufficient to keep up with that incoming data stream. So there's a handful of things there, but this was that root cause. All right, so again, wanted to show you this one because we had retransmissions. Those are ugly. It looks like network, but there was also some other things here at play. So adding that delta time and also the TCP delta time, that'll help you to sort for those, and then we can look for those delays. Okay, so this is just one example. Let me move on to another one. Got a few to work through here. Now, if we do see retransmissions, out of orders, dupbacks, that kind of stuff, what do we want to look for? We want to absolutely comb as much of the network as we own. Look for layer 2 level events. We want to look for discards. We want to look for FCS errors, CRCs. We want to look for any links that are half duplex still hanging out with collisions on them and so on. And try to clean up those that packet loss from our end. Now, here's one that I actually just ran into last week. I wanted to show it to you. Okay. I'm going to show you an example where retransmissions didn't actually indicate packet loss. Most of the time they do. TCP sent something, it didn't get a response, so it sent that thing again, right? That's a textbook retransmission. But in this case, we started to see retransmissions, and when we got down to root cause, we found that it actually was not due to packet loss. So I want to show you this. Also, this shows you the need to capture from multiple locations. Even if you can't always capture simultaneously at multiple locations, meaning the same event in 5 different places, at least move that point of analysis and get more information as much as you can. So for me, I really like working with client and server-side traces simultaneously. That's like gold to me, and also one in the middle if you can. But in this case, we couldn't get all of those at the same time, but we were able to move our capture point. So let me show you this. So just from the client side, the symptom was slowness, random slowness. Sometimes I would go out to Hotmail, sometimes go to Gmail, sometimes go to United. Sometimes it would work, sometimes it wouldn't. Sometimes it would be a flat out cannot connect, and sometimes it would just be dog slow. All right? So internet slowness was the complaint. Now, starting at capture point 1. So we started client side collecting data. Let's take a look at what that trace looked like. This is filtered just because I don't have enough time to work through the filtering process. Hang on. All right, capture point 1. Here we go. All right, so here's our SYN. We send a packet out. There's our SYN. We wait 3 seconds. If you lose your first packet in TCP conversation, guess what? 3 seconds. All right? That's human time, right? That's we don't like that kind of time. Wait 3 seconds, retransmit. Didn't get our SYNAC back. 6 seconds later, we retransmit. So right now, we're a combined total. We're 9 seconds in now. And then the connection establishes, we get our SYNAC, and then it takes off. And we're off to the races. Everything worked fine after that. So I lost the worst two packets I can possibly lose in terms of packet loss. I lost the first SYN, the second SYN, and then the third one worked. So I had a whopping total of 9 seconds of delay just waiting for this thing to connect. All right, so this is what we saw from the client side. Now, if we move our point of capture, I mean, right away, different things can start coming to your mind. Okay, maybe, is it packet loss on the network? Maybe. I mean, it's kind of weird to lose the first 2 SYNs like that, just from raw packet loss, just from, congestion or something like that. It's possible, but that's, it might. Or going through a firewall, something that even Betty mentioned it this morning when she was looking at a similar type of trace. That maybe the firewall was already busy handling so many other connections it couldn't get around to my connection and NAT it through. Or I worked with firewalls a couple of weeks ago where it had a certain number of connections allowed per user. And sorry, buddy, you've been too busy. I can't give you any more kind of thing. Like it was set to 100 connections per user, and your first 100 would work, and then after that it would say, forget it, I'm just dropping your stuff. So for me, that was actually my first assumption. As I thought, wait, we're losing outbound SYNs. Let's talk to your firewall, because it's probably your, make careful about assumptions, but I was like, let's just take a look at that firewall and see, is it have some type of a ceiling per user on number of outbound connections? Let's check that. Well, we went in and we found that number was set very high, so that was good. So what we did is we moved our capture point from the client side. We moved it outside the firewall. What I wanted to see was, are those SYNs making it through? The first 2 SYNs that you saw dropped? What happened with those? So we just took our capture point, moved it right outside, and let's take a look at those packets. We open up outside firewall. All right. Now, this is not for the exact same connection, but it was happening so much, it was the same behavior for all the connections that were breaking. All right, so this was sitting just outside the firewall. Here we have a SYN, port 443, being sent out. And do we get a SYN-ACK? We did. We saw the packet go out to whatever server. We see a SYN-ACK come back. It was being received. Well, next packet after that, packet 3, that's from the client going out. It's a spurious retransmission. Well, what the heck is a spurious retransmission? We see retransmissions, fast retransmission. What on earth is a spurious retransmission? Well, a spurious retransmission, Wireshark is telling us, I'm seeing a retransmission for something that I have already seen an acknowledgement for. It's a retransmission for something we've already seen an ACK for. So it's kind of a weird, spurious, well-named retransmission. All right? So the client sends another SYN. The client never got the SYN-ACK. So from the client perspective, it looked like outbound SYN packet loss, right? That's what it looked like. SYN lost, SYN lost, SYN worked. Okay, in this case, SYN made it to the server, got our SYN-ACK. Client never got the memo, retransmits. The next packet down, this is from the server this time. If I take a look down in our packet stuff, I can see that this guy from the server, lo and behold, this is a SYN-ACK. So the server's saying, look, that spurious retransmission, here's your SYN-ACK, buddy. Here it is again. Didn't listen to me the first time. Here's my second one. The server waits just a little bit. It sends another retransmission of that SYN-ACK. The server waits 4 seconds, sends it again. The client turns around 6 seconds after its initial one, sends another spurious retransmission. So these two are not connecting, right? Client is sending out SYNs, they're making it to the server, server's coming back. Those SYN-ACKs are not making it back to the client. All right, so where's our head start to go? I mean, firewall, but firewall, if it lets it out, it should let the response come back in, right? Should. Isn't that a great word? Okay. So we saw the reason why we moved the point of capture outside the firewall is because we wanted to see, are these packets getting out? Are those SYNs getting out, or are they being stopped right there? We just proved that they are. Stuff is getting out through that firewall. It did have enough connections available for this new connection. All right. Okay, so the next thing. So we went ahead and thought, let's just go ahead and move this guy inside here. Let's come into this third capture point. There was only a switch here. Now, it's funny because we did call the firewall people. There were some funny things in the firewall log. And the firewall people we were like, you know what? Should we just check on the inside? Let's go ahead and capture there. And they were like, it's only a switch. What can happen on the inside, right? It's just one switch you're going through. But hey, stuff happens, and in this case, stuff did happen. So you can change out the word stuff for another 4-letter word if you want. All right, inside firewall. Let's take a look now. Okay. Now this is inside the firewall. SYNs are going out. SYNs are coming back in. The switch is stopping them. It's a possibility. SYN's going out. Again, we're now inside, right? So SYN went out all the way to the server, SYN came back in. We're capturing it just as it's coming in the front door. And that client, or we see that retransmission from the server, the client sends that spurious retransmission. So from us, between inside the firewall, right behind us is just the switch and then the client. That SYN-ACK is not getting to the client. Switch is one possibility. Another is, and this is where, sorry guys, I had to filter it because there was like so much data at that point. But something we want to look at is, let's take a look at our layer 2 stuff. There was a device called, let's open up our source. Blue product 3119B5. There's our sending MAC address. That's the client that sent this. Right? Sending it to the firewall, the Sophos firewall. All right, coming inside though, Sophos is sending it to Cisco. So it's coming in from, the client is sending it out this way, but when it comes back in with just a switch between us, firewall is sending it over to Cisco device over here, some third device. Okay, that's strange. Let's take a look at our next packet from the client. MAC addresses look okay. Actual source MAC was right. Destination MAC was right. But the stuff coming back in through the firewall is going to this Cisco device. Let's take a look at what was going on. So someone just said ARP. So I'm actually going to show you, that was exactly what it ended up being. Weird ARPs, yeah, good name. Okay, in this environment, we had a device. This is just, I just, because of time, I had to kind of filter and make this look nice and concise for you. But this showed the behavior the best. We had a device, in this case, let's just say this server. It's broadcasting, it's saying, okay, 10.1.2.7, who has that IP? Because I got a packet for you, and I need your MAC address before I can send it to you. So just hook me up with your MAC address. I'll put it in the destination MAC, and we're off to the races, right? Well, check out what happens. Look how many responses we get. Does that look okay to you? So, yeah, so in this case it was a server. So, yeah, who's 10.1.2.7? And it gets 3 responses. Me. Okay, you. Whoever was last to respond gets it. So in the first case, we see a response. This is an ARP response from a Cisco device. Last 2 digits of or values of the MAC or a BB, send it back. I'm 10.1.2.7, send your stuff to me. Right after that, we see another response from another Cisco device, B3, I'm 10.1.2.7, send your stuff to me. Finally, the real guy, Apple, responds, forget those fools, I'm 10.1.2.7, send your stuff to me. When we saw that behavior, when the host was slower than those first two responses, that last updated information is what the firewall would use, and it would appropriately send the stuff to the right user. However, in some cases, you saw the next block of ARPs. Broadcast, who has 10.1.2.159? The real user replied first. The real guy was like, oh, that's me, send me my stuff. Then the other two Ciscos was like, forget that guy, send it to me. So then, in that case, the most recent information was put into the ARP table. Then the firewall would send that real end user stuff over to these Ciscos, which would kill it. They wouldn't forward it on from there. Those Ciscos were doing proxy ARP. So on those interfaces, they activated proxy ARP. They were actually VPN interfaces for vendors that this client was using to go talk directly to those vendors. Shouldn't have been using proxy ARP for what they needed it. It was overkill. That router was basically saying, I'm the whole subnet. Talk to me. Anything on 10.1.2, send it my way. I'm your guy. Problem is, it was even saying that to the firewall, right? And it wasn't keeping things in-house. It was killing the connection at that point. So there was no real purpose in having that enabled. Those two routers, pretty old dogs. They were like Cisco 800s or something. They're old dogs. We went and disabled proxy ARP. This whole problem went away. So those SYNs, TCP SYN went out, SYNAC, made it to the firewall, made it inside the firewall. Because the firewall had the wrong ARP information, it was sending it to a Cisco router rather than the end user. And after a certain number of seconds, that firewall would say, hey, where's 10.1. whatever? And that would fix its ARP table because the end user would be the last one to respond. It would get Cisco, then the actual end user, then everything would work. And these guys were having problems with their printers. They were having problems with DNS. They were having problems with everything. And it's a root cause issue, right? I mean, it's a fundamental thing, layer 2. If ARPs aren't working, if I don't have good MAC address stuff, if things aren't flowing through the switches and this type of thing isn't working, well, nothing above it is going to work either. Right? So don't forget layer 2. That's a takeaway lesson from here. It looked like packet loss. In fact, we got out a sledgehammer. We had our sledgehammer right on our shoulder, and we were about to pound that firewall really back. These guys are going down. I mean, but you know, we had enough capture points. If we had only captured client side, we wouldn't have found this. These ARPs wouldn't have been sent to us. Right? If I'm client side, I only would have seen the firewall ARP and my response. I wouldn't have seen those other routers responding as well, right? Those would have been out of the picture of my capture. So a takeaway lesson, if you have retransmissions, fully vet them. Make sure, do you see those packets coming in a certain point, not leaving a certain point, multi-point capture? Make sure we're not just relying on one perspective. And also, don't forget about layer 2. A lot of us do. I mean, we saw a transport layer problem, right? We saw retransmissions at transport layer. That led us to look down the stack. Now we want to go and make sure, how's layer 2? How's layer 3? Do not make assumptions. Don't assume, all it is between the firewall and the server, but all it is between the firewall and the client is a switch. So let's replace the switch, right? We don't want to do that. It wasn't the switch's fault. It wasn't the firewall's fault. In this case, it was routers that were completely out of the conversation that were doing proxy ARP, which we disabled. Okay, that was kind of a weird one. How are we doing on time? 2:10. I got 20 minutes. Do I have enough time? Yeah, okay. Next thing. So we talked about network issues, what we want to watch for. We want to watch for retransmissions, we want to watch for dupbacks, things like that. Also, when we do find retransmissions, we want to vet them out, make sure that we really understand what's happening at layer 2 and layer 3. Now, let's take a look at an application problem. In this case, this was an application that was running slow. It had a whole web front end that was, it had several servers on the web front end. They were interacting with a couple of different SQL servers on the back end. And in this case, we were able to look at transactions on the front end. We saw some of them were slow, not all. Of course, it's always the random ones that are the hardest. But we were able to capture on the back end and notice this. Let me come to my delta, right? This one, I went ahead and filtered on this conversation. Let's sort on delta. And I'm going to go down to the bottom. And here we have our 30-second keep alive. We saw that before. Now, keep alive, literally, as the name implies, that's just TCP trying to keep the connection alive. It's not time to kill it. It's not time to fin it. Maybe it's busy doing something else. Maybe it's not. We don't yet know. But we did see some keep alive, okay? Above that, we see a weird 13-second, this is a response from, and by the way, whenever I'm trace wrangling, thank you, Jasper, whenever I'm trace wrangling, the client is 192 and the server is 10, just so you know. It's my way or the highway, right? So I get this weird 13-second response. Now, whenever you're sorting on delta time like this, these are the types of things that you'll see. Like, you might see a long TCP keep alive thing, like 30 seconds. Now, that might be related to what you're troubleshooting or might not. If it's at the end of a conversation, let's just say you and I have a conversation, I've asked for something, you've given me that something, and then I've just waited for a while to turn off the connection or to hang up the phone. Right? It could be that those are just at the end of the connection before everything was finned or reset. We'll find out. But something you want to watch for when you're sorting on delta is just the weird numbers that really don't seem to make sense. 13 seconds on a response. That's not cool. That's people time. That's screen punching time, right? 13 seconds. We're impatient little beings. That's one that I'm probably going to sort for. So let me select on that. And I'm going to sort. Put that back in context. And check this out. Yeah. All right. So client, remote procedure call, response, remote procedure call, response. Like, these guys are moving pretty sub-millisecond. So remote procedure call, response. Remote procedure call. So here's the request. This gets sent to the server. 200 milliseconds later, and hopefully you guys can see this. Let me blow it up a little. There's my request, right? 208 milliseconds later, the server responds and says, thanks. This is just an ACK. It's just a empty ACK, 60 bytes, right? This is not an actual response. This is just TCP layer 4 saying, great, I got your stuff. Hang on. Mr. Layer 7 up there is working on it. Okay? This is not an application response. This isn't layer 7. This is just transport layer. Hey, he's working on it. Chill. So 30 seconds later, the server responds. There's one of my keep alives that we saw when we put that delta time in context. Server says, all right, 30 seconds later, hey, this is not a dead packet, but it's empty, 60 bytes. Hey, let's go ahead and keep this connection alive. This isn't a response yet. This is just layer 4. We don't want to hang up the phone. Mr. Layer 7 up there, the server, he's still working. But let's keep this connection open. So client says, sure, let's keep it open. That's cool. Client says, all right, I'll go ahead and keep my connection open, my side. So we exchange a couple of keep alives. 30 seconds later, we do it again. 30 seconds later, we do it again. We're now a minute and a half. 30 seconds later. In fact, let's come up here to our remote RPC call. I'm just going to come up here and set unset time reference. I just started a stopwatch on that request. All right, so I want my time reference, cleared that out to 0. So now I can see over here, this is the total amount of time after all of those keep alives. The server finally, 13 seconds after the final keep alive, actually gives me a response. But how much time did I wait? 193 full seconds. Okay, now I've had, I don't remember if it was exactly this one, but this type of symptom. I've had this one sent to me and said, I have a network problem. Look at all these TCP keep alives. Is this a network problem? Yeah. Ugly black lines don't always mean retransmissions, right? Ugly black lines mean, okay, you probably want to check this out, but it's not necessarily a problem with TCP. TCP is just keeping it open, but that's nice to have that ugly black because it draws our attention there, right? It tells us, hey, we got something going on here. Something's stuck. Now, those keep alives are happening between a request and a response. So that connection is staying open. If we had taken these keep alives, let's just imagine that these keep alives, if we just did a cut and paste and moved them all below that response. The request goes, the response comes back quick, and then we see keep alive, keep alive, keep alive, keep alive, response, or request, response. We wouldn't necessarily be waiting on those, or those keep alives aren't signaling a problem. It just means we're not using the connection. We're keeping the connection open, right? So keep alives don't always mean there's a problem. It really depends on where they are. In this case, we waited 193 full seconds before we heard a response from that SQL box. That's an application issue. That's where you say, look, I don't have any retransmissions. Check. No nothing else. No other TCP ugliness. There's no window issues here, right? If we take a look at the receiver, we can take in there and look at the window size and all that stuff. That wasn't the issue. Instead, we were just waiting for the server to respond. This is probably one of the longest application responses I've seen. But what happened was one of the servers in that server array was still configured to use like an old, crusty SQL box they had, where everyone else was using the big, hotshot new one. So the old crusty dog was still working on a bunch of calls, and it was just bogged down with life. And this call came in, and it really slowed down that end user. So every now and then you would get hit with this type of delay. Now for me, I was impressed that they even, we don't know on the client end, but I'm sure by then the client's already given up and closed Windows and hit force quit and started things over. After what is that? How many minutes is that? 4? So so that's what we're going to look for when we're digging for application type problems. Now for me, something that I have on my Wireshark, it's a handy little filter. If you're doing web transactions and you want to find slow web responses quickly, one filter that you can use, I just call it slow HTTP. Is what I named it, but you can add this. You can use I don't have any web in this trace file, but you can use, it's called http.time, and that filter, it's just going to be on port 80, and it shows me what is the response time between the request and the response. What is that amount of time between those two actions? And the filter name, http.time, and what I say is just show me all web responses that were slower than 1 second. That's what the 1 is. If that's 2 fast for you, you can up that number to 2 seconds, 5 seconds, whatever you want. Or if you want to be real gritty, show me all web transactions that were slower than 100 milliseconds or 500 milliseconds, whatever you want this to be. For me, I just like it at 1 second. This is a button. It's an expression that I can click. And if I'm looking for slow application responses on web servers specifically, I just click that guy and it shows me the slowest responses. So just a quick way to filter for something like that. You also notice for my buttons, I have one called No Broadcast Chatter. This is one that, for me, as I'm working through a trace file, if I see something that I'm pretty sure is not related or it's just busy on the screen, what I like to do is just get it out of there. You don't always know specifically what you're going to minutely focus in on filter-wise, but sometimes there's just chatter on the screen and you just want to get that out of there. Things like spanning tree updates, or sometimes ARP, if ARP's not related, or other protocols that you're not really interested in seeing. From there, what I do, just hit your not, and then start making your list. You want to say no ARP, or no ICMP, or no whatever. I'll say DNS. Just for whatever it is you're troubleshooting, I can say, okay, I don't know what it is, but I know those guys aren't related, so let's get those guys out of there. Or we can go and we can filter, we can add to that like a layer 2 broadcast. If I don't want to see layer 2 broadcasts, if I'm not worried about focusing in on those. What I like about that type of filter is you can quickly remove it if you suspect that ARP really is the issue, or you do need to see those broadcasts back. So that's a nice one to have as well. All right, good. Okay. All right, last one. Small delays. So you saw a big application delay. That was the many-minute SQL response. But in this trace file, if I come up here, this is just small delays, that's how I named it. Sometimes an application can do what I call nickel and dime you to death. Sometimes it's not like a massive 45-second delay that shows up real easy on all your little filters. Sometimes it's just a bunch of small ones, right? So here in this trace, what we're going to do is come in, I'm just going to sort on delta. Let's go ahead and go down to the bottom. Now usually, just so you know, instead of sorting on the actual delta, I'd be sorting, if I just started with the trace file, I'd be looking at the TCP conversation delta. Because remember that regular delta, the true like time between packets, that's going to show you everything as it relates to the packet before it, right? Not necessarily the next packet in that connection that mattered, right? Those are the timers that we want to see. So usually I'm going to sort on that TCP delta column. In this case, this is just one connection. So, all right, so what do we see? Here we can see server to client, right? These are a bunch of ACKs. These are 60-byte packets. If I come down to the TCP header, there's nothing in here. No stuff, right? This is just simply a TCP ACK. And check out the number that I see. I see a lot, right? If I scroll, there's a bunch. Now, the number 200 should be a little warning bell for you. The number 200 milliseconds, that is. In this case, this server is doing delayed acknowledgments. I'm going to show you, I'm going to put it in context and you'll see what that means. A delayed ACK means that it's waiting for more stuff to come in and no more came in, so it went ahead and set the ACK. It held the ACK back, waiting for more stuff to come in. All right, that's what a delayed ACK is. But let me put this in context and we can talk about it a little bit. All right, so client requests stuff, server responds, client requests stuff, server responds, client requests, client requests. Then we get this remote procedure call. This is the request. Then we see that 200 millisecond response. And then after that, 119 milliseconds later, we actually see the real data, the stuff, the real response from the SQL server. Okay? This doesn't seem like a whole lot, 300 milliseconds. One instance of 300 milliseconds is not a big deal. 1,000 instances of 300 milliseconds are a big deal. That's where it turns into you punching your screen, right? So if we take a look at a bunch of smaller delays, here we can see that this SQL server, we get a request, we see a delayed ACK, we see an actual response with real stuff. Up above this, you can see the same behavior. Here's a request. You can see a delayed acknowledgement. Then you see an actual response with real stuff. And this pattern just kept happening. Well, the 200 milliseconds at first, you might think, oh man, why are we waiting 200 milliseconds to respond? But in fact, in this case, the application wasn't ready to respond anyway. From request, here let me time this actually. From the request to the actual data coming in was a total of 326 milliseconds. From request to response. In the middle of that, the server hadn't responded or hadn't gotten around to actually getting that response back anyway, so it delayed the request. It delayed the TCP acknowledgement. It could have been that more was coming in from the client, especially if we have a small packet. If we have something smaller than the 1500 byte or the 1460 to be exact, then it could be that more is coming, so why don't we just delay this because my server's not responding anyway, so we're going to delay this acknowledgement. It waited 200 milliseconds, it delayed it, then after that the server response comes. So for me, I'm not super worried about that delayed ACK because if you look at the rest of them, they happen pretty quickly. Instead, what we did is we went in and we found out, I cut the data off, but we found out what call was being requested, and it constantly was slow, that specific call. So the DBA got in there and was like, oh, he made some little tweaks, and then this delay went away. But in this case, what I'd like you to take away from this trace is that little teeny delays can add up. So it's not always going to be this big honking 60-second thing that's just so clear as day in your trace file, right? Sometimes it's going to be down to these smaller delays that persistently happen. And those are the ones that you want to take a look at. And again, something like this, let me unset my time reference. This is interesting to look at with your Stevens graph as well. In fact, let me pull that up. I just clicked on a packet from going in that direction from server to client. And let me look at my Stevens graph. And you see all these little delays. Let me zoom in here. So basically those are sequence numbers. So that's data coming to me, and then a wait, and the data coming to me, then a wait, and data coming to me, then a wait. So those are all smaller application delays. So those are also some things you can find with applications, and then you want to get in and take a look at what exact call is going, and then work with your DBAs and figure out what's exactly causing that to be held up. All right, guys, I do have another example to show you. It's one of those TCP weirdness ones that I found once. It slowed things down, and it got down to the nitty-gritty of TCP. I've run out of time in this session. I'm going to be repeating this session tomorrow afternoon, but instead of going over the SQL stuff, I might just go straight into that TCP weirdness. That's what I like to call it. So anyway, I appreciate you guys coming, and enjoy the rest of your Sharkfest today.